All right, need to talk about something kind of totally different right now. We're going to go here and talk a little more about limits. And the rule we're going to talk about here, it looks like El Hospitals, but usually that's pronounced L'Hôpital. It's a French guy. L'Hôpital. L'Hôpital's rule for limits. You know, back when we were doing limits, we had various, we did conjugate, we did the conjugate thing, sometimes we did factoring. Yeah, so just kind of recall here, if we've got this. Denominator goes to 0. All right, so, okay. No problems there because this one, we can work this one by factoring. All right, well, remember we did that. Factor off the x, factor the bottom one, difference of squares. Yeah, this one works out by factoring because of the fact that, common factor, so I can cancel that out. And so that's going to be equal to the limit as x approaches 1, x over x plus 1. I can plug in then the x to be 1. Turns out it is 1/2. However, and then, you know, some of them you can use a conjugate technique, or some of the others. I'm drawing a blank on the others right now, but we had various techniques. Oh, combined fractions, different ways of working things. However, I don't think we've worked. We would be able to work one. Say we had the limit x approaches 1 of ln of x, x minus 1. We didn't come across one of those yet because we hadn't talked about ln yet. But anyway, can we factor that one? I don't think so. No factoring can be done there. Conjugates, we used that when we had the square root somewhere on it. Combined fractions, well, there's not really fractions to combine, so we're kind of at a loss here, but again, we can't plug in. Plug that in. So that's where, for one's, another technique we can use for some of these is it's called L'Hôpital. L'Hôpital's rule. L'Hôpital's rule it's actually going to be valid only for certain determinate forms. So it's valid for the indeterminate form. We haven't talked about these yet, but there's two types. It's valid for the indeterminate form 0 over 0 or infinity over infinity. Here's what I mean by that. This little limit right here is the form, indeterminate form 0 over 0. In other words, it's a limit that appears to be indeterminate because you have 0 over 0, right? Because if I plug in x to be 1 in the place top and bottom there, well, as x approaches 1, this goes to 0, doesn't it? And we haven't talked a whole lot about the natural log yet, but as x approaches 1, if you plug in ln of 1, plug that in and see what you get. Different ways you can see it, but yeah, if you just plug in ln of 1 into your calculator there, you get 0. This is what is known as the indeterminate 0 over 0. An example of infinity over infinity, if I have limit as x goes to infinity of the ln of x over x minus 1. This is an example of infinity over infinity because as x goes to infinity, well, you have infinity minus 1. That's certainly infinity. The ln, as x grows larger and larger, so does the natural log. So that also goes to infinity. So essentially, yeah, this just as is, the top's going to infinity, the bottom's going to infinity. Okay, so this is what is meant by 0 over 0, infinity over infinity. It's just what the values go to, numerator and denominator go to. Okay, so here is L'Hopital's rule. Suppose for the limit as x approaches something, call it a, f of x over g of x. Suppose for that limit you have the indeterminate form (0 over 0) or infinity over infinity. If that's the case, then L'Hopital's rule states this. The limit as x approaches a of f of x g of x is equal to, now catch this, is equal to the limit as x approaches a of the derivative of f of x over the derivative of g of x, f prime over g prime. What this means is, let's start with the first one we had up here. The limit as x approaches 1, ln of x over x minus 1. First thing, right off the bat, you've got to see if you can use L'Hopital's. And again, it has to be 0 over 0, infinity over infinity. If it's 1 over 0, no go. If it's 1 over infinity, well, you wouldn't want to use L'Hopital anyway, but anyway, we'll cover some of that ground here in a second, but this is 0 over 0, right? And so what this means is I can now, by L'Hopital, take the limit x approaches 1, instead of ln of x over x minus 1, I'm going to take the derivative of ln of x, which is 1 over x, and the derivative of x minus 1, which is 1. I'm going to do that new limit right there. L'Hopital says I can do that, since it's 0 over 0. Now, why would I want to do that? Well, notice now, can I do that limit? I can do that limit, can't I? As x approaches 1, this goes to 1. Of course, that goes to 1. L'Hopital tells me the limit of ln of x over x minus 1, it's going to be 1. So it's a little something different we can do when we have 0 over 0 or infinity over infinity. All right, well, we had an infinity over infinity. All right, so if x went to infinity, same things, but this was infinity over infinity. Well, infinity over infinity, it tells me that also I can use my L'Hopital. And by L'Hopital then, it would be the limit as x approaches infinity of 1 over x over 1, which, let's think about that. That's the same as, it's not quite as quite the same there, but we've done these before, right? This is now doable. I mean, it's 1 over infinity, but what do we come up with on 1 over infinity? It's 1 divided by a larger and larger. When I have 1 divided by something that's growing infinitely larger, isn't that 0? Because 1 divided by 1, 1 divided by a million, 1 divided by 1,000, 1 divided by 1,000, 1 divided by a million, 1 divided by 10 million. Yeah, this is going to go to 0. 1 divided by infinity is 0. So what started off something I couldn't do because of, infinity divided by infinity is not 1. Turns out in this case it's 0. 0 divided by 0, well, it turned out to be 1, but yeah, we can do what some things with L'Hopital now if we've got those. So let's just look at several examples and see where this all goes, okay? Here's some more examples. Limit as x approaches 0, 3x minus sine of x over x. Well, again, something we couldn't have tackled previously, but now with L'Hopital we can, because notice L'Hopital applies, because remember, for L'Hopital you got to have 0 over 0 or infinity over infinity. What do I have here? Well, if x goes to 0, that's 0, 0, 0. So it's 0 over 0, isn't it? So by L'Hopital, I can say this is the limit as x approaches 0. I do the derivative of the top, derivative of the bottom. So the derivative of the top would be 3 minus cosine over 1. So if we do that, a lot of times then it gets us down to a form. We can evaluate a it is something we can determine here, because we're to now a place. If I then, can I evaluate this limit? Because I'm no longer indeterminate. If x goes to 0, doesn't this go to 3 minus the cosine of 0? What's the cosine of 0? Cosine of 0 is 1, isn't it? Turns out this is 2. How about that? The limit as x approaches 0 of that function right there is 2. All right? Now, where you need to be careful is note this one. L'Hopital here doesn't apply. I know. Got the bottom as 0, don't I? But what about the top? Top's going to 1. This is 1 divided by 0. Top's going to 1. Bottom's divided by 0. L'Hopital doesn't apply there. So if you put L'Hopital to that, you're going to mess up. 1 divided by 0, you can't use L'Hopital with that. It has to be 0 over 0. This one we'd have to do some other way. But I just wanted to point out there, that would not give you the correct answer if you did L'Hopital there. Okay? All right. All right, what about the limit x approaches 0, x minus sine of x over x cubed? Can I L'Hopital it? That's 0, that's 0, yeah, 0 over 0. So we have another L'Hopital. So let's do the derivative. L'Hopital says then I can take the derivative of the top, which would be 1 minus cosine x. Looks a lot like the previous one, but the bottom is 3x squared. Okay. Can we evaluate that? X approaches 0. Well, we can try plugging in x to be 0, so that would give us 1 minus the cosine of 0, which is 1 minus 1. The bottom is 0. Don't I get 0, 0 again? I get 0, 0 again. So guess what? L'Hopital again, yeah. You can apply L'Hopital multiple times. So we're going to L'Hopital this thing again. Derivative of the top, well, the derivative of that would be 0 minus the cosine, so that would be positive the sine, wouldn't it? Derivative of the top would be positive sine. Derivative of the bottom would be 6x. Guess what? 0 over 0 again, isn't it? Sine of 0 is 0, 6x. That goes to 0. So we're going to L'Hopital a third time. That would be cosine of x over 6. Aha! Cosine of x, what does it go to? 1. 6 goes to 6. It's 1/6. X minus sine of x over x cubed, the limit is 1/6. Probably would not have guessed that if you'd looked at that. So yeah, you can do L'Hopital multiple times so long as you've got an indeterminate form, 0 over 0 or infinity over infinity. All right. So far, well, these last few anyway, have all been 0 over 0. So let's look at some infinity over infinity. What about the limit as x goes to infinity, x squared over e to the x? Well, that is infinity over infinity, isn't it? A little something different. The top, infinity squared is infinity. E to infinity, well, e to a power, if your power is growing bigger and bigger of e, certainly e to a power that's getting bigger and bigger and bigger is infinity, right? So it's infinity over infinity. So we can L'Hopital this. So this will be the limit as x goes to infinity of top derivative would be 2x, the bottom derivative, the derivative of e to the x, e to the x. So now I have the limit as x goes to infinity of 2x over e to the x. What have I got there? Well, the top's going to go to infinity. 2 times infinity is infinity. E to infinity is infinity. So I still got infinity over infinity. So one more time, L'Hopital. L'Hopital one more time. That would be 2 e to the x. So now I have 2 divided by e to the x. X goes to infinity. What about that? Let's think about that. This is now, the top is going to 2, so it's not infinity over infinity again, but it's 2 over infinity. It's 2 divided by something that's getting bigger and bigger and bigger and bigger. What's that going to go to? 0, isn't it? Yeah, if you have a number divided by something going to infinity, that's always